Alright, so this is more about section 10.6, which is on power functions, or power series, actually. And in class, we did some work on finding the radius of convergence and the interval of convergence with power series. And now we're going to kind of take a new approach and do something else with power series that leads to a way to use these power series in a way that's helpful to us. So the idea is we're going to start with a function. So a function that maybe we already are familiar with, like e to the x or sine of x. And we're going to take that and we're going to make it into a power series. So we're going to turn a function into a power series. So it may seem like we're making it more complicated, but hopefully as we work through some of these questions, you'll see that these power series actually are things that are pretty easy to work with as compared to things like e to the x or sine of x or 1 over 1 minus x. One thing to first notice is that all polynomials are their own representations as power series. So if you have a polynomial like x squared plus 7x plus 5, that is itself a power series because it's really a series with an infinite number of zeros added. So you can think of it as a power series for itself. So polynomials are their own power series. So we have a whole class of functions that we already know their power series, and our goal over the next few sections is to find power series representations for other functions. So the first one you'll see here, the very first one that we'll deal with, and this is kind of our big focus over all these sections, that this first section is to think about 1 over 1 minus x. And you'll see this equation right here that 1 over 1 minus x is really just the sum of x to the n. And hopefully you remember this from, or this looks familiar, if we think about the geometric series. So remember the geometric series converges if the absolute value of x is less than 1. So this only holds if the absolute value of x is less than 1. And if that's the case, then we have 1 over 1 minus x is equal to that power series, because if you remember, this would be our r, would be x in this case, that's our radius, and if you remember, if a power series, or if the geometric series converges, it converges to a, which in this case is 1, over 1 minus r, and in this case x is r. So we have a power series representation for 1 over 1 minus x using the geometric series, and that's how we can have that representation. So then the idea is, can we find power series representations for other functions that look like 1 over 1 minus x? And in particular, we know we can just start with functions maybe like 1 over 1 plus x, right? So we'll start with this one first. Down here is letter A as our first example. And if you think about 1 over 1 plus x, that's really the same thing as 1 over 1 minus a negative x. And so if we're looking back at our power series representation, this is pretty much the same thing as what we had before, but instead of plugging in x, we'll plug in negative x. So we're still going to sum n equals 0 to infinity. But now we'll just start at a negative x because that's what is here, right? As opposed to just a regular x in the original power series representation that we were given. And then it's always nice to simplify these in a way that looks easy to understand. So in this case, we have negative 1 to the n, x to the n. And that would be the power series representation for 1 over 1 plus x. And again, these are all going to have sort of intervals and radius of convergence. And so we want to be careful of thinking about that. Like, this isn't always true for every x, but it will be true for some x's. And we can find out where in a little bit. The next power series we're going to look at is x over x plus 1. And again, the idea is we only have one power series representation at the moment. So our goal is going to be to try to rewrite this as something that looks like something we know. So we could do x is equal to x times 1 over 1 plus x, which is x times 1 over 1 minus a negative x. And then we know the power series representation from that, from the last question. So we have x times the sum from negative 1 to the n, x to the n. And then we can bring that x inside the sum. So we have one final sum as our answer. N equals 0 to infinity, negative 1 to the n, x to the n plus 1. So that's our power series representation for x over x plus 1. And then the last one we have here, this is the first one that gets like sort of the most complicated of the three examples that I have here. So this is 1 over 3 plus x squared. And as you first look at this, the first thing hopefully that you'll notice that we need to take care of is this 3, because we don't have 1 over 3 minus x, we have 1 over 1 minus x. So the first thing we're going to do is get rid of that 3. And the best way to do that is to multiply the top and the bottom by 1/3, and that will take care of the 3 in the denominator. So we have a 1/3 here, a 1/3 on top, and then a 1 plus x squared over 3 in the denominator. And so hopefully now we can go ahead and write out the power series for that. So we have 1/3. This is the sum, n equals 0 to infinity. Here's our 1 minus something, and in this case we have x squared over 3. And remember, it is negative in this case because it's plus and not minus. Remember, the power series representation that we know is for 1 over 1 minus x. This is a plus, so the plus turns into a minus, and this is what we have plugged in there instead of an x. And then now we just want to simplify this. We want to write it as one final sum. We'll see that we have a negative 1 to the n, x to the 2n, so that's taking our n and taking it into those first two terms. We have a 3 to the n in the denominator, as well as this additional third on the outside, so that 3 is also in the denominator. So it looks like we end up with 3 to the n plus 1 in the denominator. So there's your power series representation for 1 over 3 plus x squared. So that's the first thing we'll do, is look at functions that look like 1 over 1 minus x, manipulate them until we get it to look like 1 over 1 minus something, and then you'll plug that into that power series representation for 1 over 1 minus x, simplify, and get a power series representation for your new function. This is pretty limiting, and so what we're trying to do now is maybe come up with some ways to find further representations of power series representations for functions that don't look exactly like 1 over 1 minus x. What we do is use this following theorem that we'll go through very slowly to make sure that we understand what it's saying. So this theorem says that if the power series, the sum of an, x minus c to the n, has radius of convergence r, so we know the series converges, right, for some particular radius, then the function defined by f of x is that power series starting at 0 going to infinity of an x minus c to the n. That power series representation of the function is going to be differentiable on the entire interval of convergence, c minus r to c plus r. And if we look at this is just a whole bunch of power functions added together, and it turns out that we can take the derivative in just the way that you would like. So if we look on the inside here, we bring down our power n, and we have x minus c raised to the n minus 1, and then obviously the derivative of the inside is 1, so we don't have to change that. So we just took the derivative of this power function, brought down our n, subtracted 1 from the exponent. Everything else is constant, so we don't have to take those derivatives. And if we notice here in the front, we don't really need n equals 0 anymore because we have this thing starting at n. If we plug in 0, we're just going to get 0 anyways, so we'll go ahead and start this at 1 instead of 0. That also helps in terms of having this subtraction power. We don't really want to have negative exponents in our power series, even though it is times 0. Just to be careful in terms of making sure we don't have a denominator we can't have. So the derivative there is just taking down your exponents like you would. And it also turns out that you can integrate these power series in the same way that you would integrate any power function. So if we want to integrate, obviously we can do this, an, and then we'd have x minus c, the new exponent, we would add 1 to our exponent over n plus 1, and then we would divide by n plus 1, and then we'd add a for some constant, right? Because this is an indefinite interval. So those are two new ways to find power series. So we can find power series by just starting with the function and kind of manipulating it slightly to get almost exactly what we want. Or we can think about maybe a function is the derivative or the integral of some function that we already do know its power series, and then we just integrate or differentiate that power series to get the power series representation for the function that we are interested in. And we're going to look at a couple of examples of this next, so we have a way to do that process. One quick note when we're starting to think about radii and intervals of convergence if we substitute a function of x into one of these power series representations, we're going to get a new power series with possibly a different radius of convergence. But you'll notice for these two here, where the derivative and the integral, the radii of convergence of both of these is still r. So when you take the derivative of one of these things, you still get the same radius of convergence as you would for the original power series. And if you also think about, if you do substitute a function in, right, so if you're not doing 1 over 1 minus x, if you do something like 1 over 1 minus x squared, right, so if you plug something in that's a function of x, that's not just x, then you may actually change your radius of convergence. So differentiating and integrating does not change your radius of convergence, but substituting some function of x in definitely could change your radius of convergence. So let's look at this example, which is slightly different than the ones we were doing earlier. This is negative 1 over 1 plus x squared, and we would like to find a power series representation for this function. So if we wanted to do that, the first thing we can think about is the fact that this, hopefully, is the derivative of something that we know. So that's going to be our goal, because it's definitely not just 1 over 1 plus or minus something. But it does look like 1 over 1 plus x, but it's just got this negative and a squared. And if you think about it very carefully and look at it for just a minute, you're just trying to think about going backwards, I'm pretty sure that this is just the derivative of 1 over 1 plus x. Right? Because if we take the derivative of 1 over 1 plus x, we're going to get the negative from the negative 1 in the exponent for the 1 plus x, and then we're going to subtract 1 from our exponent and get negative 2, which goes to the denominator. So then we can start to write this power series representation. This is just the derivative of negative 1 to the n, x to the n, from 0 to infinity. And if we do that, we're going to have the sum n equals 0 to infinity, negative 1 to the n, n x to the n minus 1. And in fact, we can change this thing from starting at 0 to starting at 1, since we took a derivative and we know we won't have that n equals 0 term. So there's the power series representation for negative 1 over 1 plus x squared. So that was one where it was more or easier or faster to do the power series representation by taking the derivative of something we already knew the power series representation for, and then taking that derivative of the power series to get a new power series for this thing that is not exactly 1 over 1 plus x, or 1 minus x. All right, one more example just to make sure we feel good about using integrals and derivatives to find power series representations of functions. And so this one is asking about the power series representation for arctangent of x over 3, and then we're supposed to determine the radius of convergence for this as well. So the first thing is to think about arctan of x over 3. Well, that is not exactly a function that I'm going to be familiar with. And so the thing is to think about, well, what is arctangent of x over 3 close to that looks like a 1 over 1 minus x? Because remember, that's the only power series representation that I have. So what is this close to? So I'm pretty sure it's just the integral of 1 plus x over 3, that quantity squared. Right? If I integrate that, that would be arctangent of x over 3. And then we have to think a little bit about constants here, so we need to be a little bit careful about where our constants go. So in this case, we would want to make sure you're going to, when you're taking what we're really doing is taking the derivative of arctangent right now, and the derivative of that would also give us a 1/3 as the derivative of the inside piece of this. So that's what we would be integrating as we were to find the power series representation for this function. And if you think about integrating this, right, u would be x over 3, the derivative of that would be 1/3, so all that would go away and you'd just be integrating 1 over 1 plus u squared, which we know is arctangent. So it's this idea of kind of going backwards and thinking about, well, what does that look like? It's pretty much just the integral of this function here. But hopefully that's recognizable. We can take the 1/3 out, and now we have 1 over 1 minus negative x over 3, that whole thing squared. And so if we want to turn that into a power series, we're integrating the sum of negative x squared over 9, or we can say 3 squared maybe, to the n. That's our power series representation, right? Because we're 1 minus this junk here, and that's the junk that we're going to plug in for raised to the n. So we'll put our 1/3 outside. We'll go ahead and maybe simplify this before we integrate it. This is negative 1 to the n, x to the 2n over 3 to the 2n. And if we integrate this, looks like we'll get 1/3. We'll have a summation sign, negative 1 to the n. X will be to the 2n plus 1, right? We'll add 1 to our exponent. We'll have the 2n plus 1 in the denominator as our new exponent, and then we'll also, or as the new exponent in the numerator, and then we'll still have the 3 to the 2n because it's a constant here, right? We're integrating with respect to x. And then don't forget your plus c, your constant, with this situation. So there is this function power series representation that has been worked out. The last thing we'll do on this slide before we continue is go ahead and solve for c. So we need to know what c is because we want the official power series representation. We don't want a generic one. But we know that arctangent of x over 3 is equal to this whole thing. So if we let x equal, and you can choose whatever number you want here, but I'm going to choose 0 because that's something that's easy for me, then I know that arctan of 0 over 3 is equal, if I plug in 0 on this side of the equation, then I'm going to get a 0 right here. So that's just a sum of a whole bunch of zeros. So that's going to be a 0 plus c. Arctangent of 0 is 0, so I get 0 is equal to c. So I know that I actually don't need this c here, and that's kind of what helps us decide on what our series is. The other thing I should be probably a little bit careful about is making sure I have these bounds on the series all the way through, just to make sure I know where this series is starting and beginning. So we're pretty close. We have a final answer, I think, now for this power series, arctan of x over 3. I think we got was the sum. We still have a 1/3 out front, n equals 0 to infinity. We're going to put negative 1 to the n, x to the 2n plus 1. We're going to divide by 2n plus 1, and then we're going to have a 3 to the 2n. And remember, the constant goes away because we decided it was 0. So we can do one more thing here to make it a series without having a constant in front. X to the 2n plus 1 over 2n plus 1, and this is 3 to the 2n plus 1. So now the very last thing that we need to do is calculate the radius of convergence. So remember, for that we're going to probably use the root test or the ratio test. And here this looks pretty much very much like the ratio test. So we're going to go ahead and do the ratio test here. So it looks like we get negative 1 to the n plus 1, x to the 2 times n plus 1 over 2 n plus 1 plus 1, and 3 to n plus 1 plus 1. All that is times 2n plus 1, 3 to the 2n plus 1, all over negative 1 to the n, x to the 2n plus 1. And remember, we're taking the limit as n goes to infinity of this. So we're pretty close here. Let's see. These negatives will cancel because of the absolute value sign, so we don't really need to worry about the negative 1. And then let's look at our powers of x. If we simplify this thing here, it looks like it's 2n plus 3 for this exponent here, and then this one's 2n plus 1. So if we simplify that out, it looks like we would have an x squared in the numerator, because there's going to be 2 more of those in the top than there are of those in the bottom. We're going to be left with a 2n plus 1 on top and a 2n plus 3 on the bottom from these pieces right here, foiling all that out. And then I think we'll also end up with a 3 squared from these pieces right here, because they're going to foil out in a similar manner where you're going to have, this is going to be 3 to the 2n plus 3, and so you'll end up with an extra squared down there. And so if we take the limit as n goes to infinity of this, we're going to use L'Hopital's rule here. We'll get x squared over 9 times 2 over 2 with L'Hopital, and we're still going to be taking the limit at this point because we just did L'Hopital's, but everything's constants. So we'll end up with x squared over 9. And if we get x squared over 9, then what we end up with is that we need x squared over 9 to be less than 1 in order for this to converge. And if we work all that out, take the 9 over, take the square root with these absolute values, we'll get the absolute value of x has to be less than 3. So remember, in order to find the radius of convergence, which we just found to be 3, so we get that r equals 3, you have to get x by itself. So we needed to take the 9 over, which we did, and then we took the square root of both sides to get the 3. You don't need the plus or minus because that's what the absolute value signs are doing for you. And so we get a radius of convergence of 3, and we have a power series representation for this function.